Hello and welcome to our lesson on radical expressions. So this is going to be the start of a pretty short module about radicals. We're going to start with expressions, we'll look at rational exponents and how they connect to radicals, and then we'll finish up the unit by looking at radical equations and radical functions. But it all should be pretty quick, and then we're going to be preparing for the midterm, okay, just to keep that on your radar. Alright, so radical, I know we have experience with radicals before, but just so we have some terminology in place, when we're looking at this first radical expression that I've got on the note paper here, there are three components to this, so three terms involved in those three components that I want you to make sure that we are all clear on. So obviously the little symbol, this guy here, is going to be our radical symbol, and we can also call it a root symbol, okay? And then I think we may know that the part that is underneath the radical, so in this case A, has a name as well. The part underneath the radical or the root we're going to call the radicand or radicand. I like radicand, but if you want to say radicand, that's fine too. And then the n here, which we don't always see. You know, if it's just a square root, we don't see any number written right there. But if we had a cube root, we'll see a number written there. If we had a fifth root, we'd see a number there, or a fourth root. Or any number beyond 2, we're going to see the number actually written there. That number we call the index. So that is called the index of the radical. And the index can vary depending on what root we're looking for. But there is a restriction on it. Well, there's two restrictions. It has to be a whole number, so we're not going to have an index that's, let's say, a fraction. And it has to be at least 2. So we can't have like a first root. The smallest root we can take is a square root. So the index, the smallest index we can be looking at is a 2. Or we can take a cube root or a fourth root or fifth root. So it's got to be a whole number and it's got to be at least 2. So we want to say here that our index n has to be greater than or equal to 2, and it has to be a whole number. Okay, so we're not going to be dealing with any decimals or fractions in there, and it's got to be 2, 3, 4, 5, 6, something like that, and up. And when it's a 2, we're not going to see it. Okay, so I think we know this, but just to be clear. Now, there are three things that we should be able to do with just a radical expression. We should be able to evaluate. That means find the exact value if one exists. We should be able to estimate. That means approximate the value if an exact value doesn't exist, or simplify. And the simplifying is going to be the probably most important piece of the lesson today. Okay, so let's look at evaluating first. I like evaluating because really it's something that you can do with a calculator if you're not super comfortable with it, but I'm hoping that everything that's on the list here we can do without a calculator. So for example, the square root of 25 we know is hopefully 5, and we know this because the square root of 5 is saying what number can we multiply it by itself to get to 25, and that happens to be 5. What about the square root of negative 25? So the question would be, is there a number I could multiply by itself to make a negative 25? Well, my options would be a positive 5 and a positive 5, which would make a positive 25, or a negative 5 and a negative 5, which would still make a positive 25. Since this number has to be the same number twice, and since a positive times a positive makes a positive, and a negative times a negative still makes a positive, then this doesn't exist. This is not possible. So we're going to say this does not exist. Does not exist. Or we could say that there's no real number value for it. When we get to imaginary numbers, which we'll talk about in the next module, then we'll be able to simplify something like that, but we cannot evaluate it. There is no real number value for a negative square root. So that does not exist. Now if we move the negative on the outside, this is saying multiply the square root of 25 by a negative 1. So we know the square root of 25 is 5. Well, we can definitely multiply by a negative 1. So this answer is going to be a negative 5. And then on the next guy here, the double negatives, sometimes we see those and want to make that a positive. But this is saying, take the square root of negative 25 and multiply what you get by a negative 1. Well, I can't multiply something that does not exist by a negative 1. Okay, so this still does not exist. And we are going to abbreviate that to D, N, E, so we don't have to keep writing out those words. Okay? Now how about a cube root? A cube root of 27 is asking you what number could you multiply by itself 3 times in order to get to that radicand. So in this case it's going to be 3. 3 times 3 would make 9, times another 3 would make 27. So the cube root of 27 is going to be 3. Now what about the cube root of negative 27? Do we have the same issue with the negative here that we had with the square root of negative 25? No, because if we multiply a negative 3 and a negative 3, I'd get a positive 9. But if I multiply by another negative 3, then I would get a negative 27. So this is going to be a negative 3. Here, cube root of 27 we said was 3. If we multiply that by a negative, we're going to get a negative 3 again. And then here, so this was a negative times the 3. The cube root of negative 27 would be negative 3. If we multiply that by the negative on the outside, that's going to make this one a positive 3. Okay? Now, if you weren't comfortable with those, or if you just wanted to double check your work, remember your calculator is going to do all of this for you. So the square roots, I know you know the square root of 25 is 5, but let's just say that you weren't sure about the negative underneath the square root. So your calculator is going to tell you it's undefined. Undefined, does not exist, no real number. Those are all sort of saying the same thing, that it's not possible to take the square root of negative 25. And then if you weren't sure about the negative on the outside, again, you could check that. And then maybe the square roots were comfortable with. The cube roots, if you weren't so much. Cube roots are not on the home screen here, but if you hit the functions key and go to miscellaneous, toward the middle here there's this button with an N, okay, with the nth root, where you can make the index whatever you want. So the cube root of 27, or we can take the cube root of negative 27, or we can do a negative cube root of negative 27 and confirm all of that work. Okay, and that would be really helpful for maybe something like the next one. If you weren't sure, let's say the 4th root of 81, that's what number are you multiplying by itself 4 times to get to 81? Well, that's going to be 3 again. 3 times 3 is, that should make sense. That's going to be 9. That's going to be 9. 9 times 9 is going to get us that 81. Again, if you weren't sure, 4th root of 81, again, functions, and then miscellaneous. So let's do the 4th root of 81 just to confirm. And that's going to be, again, 3. So this is going to get us 3. And what's going to happen if we put in a negative with that 81? Well, that's, again, going to be undefined. This does not exist for the same reason the square root didn't exist. If I have an even root, I'm looking to multiply a number by itself an even number of times. Whether I have 2 negatives or 2 positives, I get a positive. Whether I have 4 negatives or 4 positives, the result will be a positive. There isn't a way to multiply an even number of positives or negatives and get a negative result. So for the same reason the square root doesn't work, the 4th root's not going to work here. Now if I put the negative on the outside, that's not an issue. That's take the 4th root of 81, which we said was 3, and multiply it by the negative, so we get a negative 3. And then here, again, this doesn't exist, so we can't take something that doesn't exist and multiply by a negative, so this whole thing still is undefined. It doesn't exist, it's not possible. Okay, how about 5th root of 32? Do we know this one? What are we going to multiply by itself 5 times to get to 32? Well, it's 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is going to get us that 32. So the 5th root of 32 is 2. And again, if you aren't sure, let's just put it in here. What is the 5th root of 32? It's 2. Okay? 5th root of negative 32? Negative 2 times a negative 2. Let's use parentheses because that's becoming a mess. If I multiply a negative 2 and a negative 2, I get a positive 4. Times a negative 2 is going to make a negative 8. Times a negative 2 is going to make a positive 16. Times a negative 2 is going to make a negative 32. 5 negatives make a negative. So the answer here is going to be a negative 2. And again, if you weren't sure, put it in the calculator. It confirms. So this is a negative times the 2 here, so negative 2. And this is a negative times the negative 2, which makes this one a positive 2. Okay? So these are, again, hopefully things that you can do without the calculator, although the calculator can confirm them all. But there are a couple of takeaways here. First of all, when the root of a number has an exact value, like the ones that we just looked at, then we should be able to evaluate with or without the calculator I would prefer the without, but it's really okay if you need to rely on the calculator. But more importantly, if you're taking an even root, and when I say an even root, what I mean is the index of the root is even. So this would be an even index. So a square root, a fourth root, a sixth root, and so on. If you're taking an even root of a positive number, like the square root of 25, okay, or the fourth root of 81, that is an even root of a positive number, then what do you get? You get a positive result. Okay, so even roots of positive numbers are positive. But what happens when we have an even root of a negative? So if it's a square root of a negative like this, or a fourth root of a negative like this, then we can't, it's undefined. We cannot take an even root of a negative because, again, an even number of positives or negatives is not going to produce a negative. So even roots of negatives do not exist. They are undefined. There is no real number value for them. Okay, so even roots of positives, again, just so you can connect these, that would be like this guy. Okay, or even roots of negatives. Even roots of negatives would have been like this one. Okay, now odd roots are unrestricted. An odd number of positives makes a positive, an odd number of negatives makes a negative. So odd, let's go another color, odd roots of positive, that's not what I wanted, I'm sorry. Odd roots of positive numbers, like the cube root of 27, is going to make a positive result. So odd roots of positive numbers are positive. And odd roots of negatives, an odd root of a negative is going to be negative. Now I just got to fix my highlightings. And again, when I say odd roots, I mean there is an odd index for the root. And this odd number, son of a gun. Odd roots of negatives are negative. And I should have highlighted that. And I should have highlighted that. And lastly, that, just so it all connects. Okay? So even roots of positives are positive. Like 3 out of 4 of these, they make sense. Okay? Even roots of positives are positive. Odd roots of positives are positive. Odd roots of negatives are negative. The only one that's weird, is this guy right here. Okay? This guy. Even roots of negative numbers. They do not exist. And that star was terrible. This is the weirdo right here. Okay? Even roots of negatives. The only one you got to watch out for. But again, all of that could be confirmed with a calculator. Okay? Now, if, I don't know why we wouldn't have a calculator, but if we didn't and we wanted to estimate an imperfect root, right, when the root of a number is not exact, we could just estimate it or approximate it with a decimal. It could be estimated or approximated with a decimal. Again, with or without a calculator. Obviously, with the calculator is going to be easy or easier, but we should be able to approximate like the square root of 20 without a calculator. And how would we do this? Well, you'd have to know that which perfect roots the radicand is between, as well as which of those two it's closer to. So, for example, I don't know exactly what the square root of 20 is, but I know the square root of 16 and I know the square root of 25, and 20 is right between those. So I know that the square root of 16 is 4 and the square root of 25 is 5. And so since the square root of 20 is between the square root of 16 and the square root of 25, the decimal approximation for 20 has to be between 4 and 5. Now it's 4 units away here, and it's 5 units away from this one. So since it's a little closer to the 4, the decimal value is probably going to be a little closer to 4 than 5. So if I was going to approximate this without a calculator, I would say it's probably about 4.4, and that's just a ballpark. Okay, helpful to be able to have in your head an approximation sometimes without having to run to the calculator all the time. So let's just verify. Square root of 20 There you go. It's about 4.47. So calculator confirms maybe 4.5 is better, but whatever. It's an approximation. Okay. So again, if let's say we wanted the cube root of 65 without a calculator, we got to know what it's close to. Well, I know the cube root of really huge. I know the cube root of 64 is going to be 4. 4 times 4 is 16, times another 4 is going to make 64. And I know the cube root of 125 is going to be 5. And because the cube root of 65 is between those two, my decimal has to be between 4 and 5 again. And this time, we're really close to 64. So my decimal is going to be really close to 4. So without a calculator, I'd say this is going to be probably around 4.1 or 4.0 something. Let's just confirm it. Let's see, what is the cube root of 65? There's 4.02. Okay, so 4.1 would be a perfectly reasonable approximation without a calculator. Okay? So we got to be able to evaluate if it's perfect, estimate it if it's imperfect, and then we have to be able to do this part, the simplifying. Okay? Simplifying a radical means it's imperfect, but there's a perfect root hiding in the imperfect. Okay? When we're simplifying a radical, you're still going to have a radical in your simplified answer. So I just want to deviate here for a second. Something like the square root of 50, square root of 300, square root of 18, all right, these are examples, but I want to show you with something that's perfect first so you understand the concept we're going to use to simplify, okay? So we know the square root of 100, the square root of 100 is 10, right? But let's just go for a second here. Would you agree that this is the same thing as the square root of, let's say instead of 100, I wrote it as 25 times 4. Would that be any different? Well, hopefully not. 25 times 4 is still 100 under there, right? So if I separated the 100 to 25 times 4, I've not changed anything. That's still 100. But could I separate it this way? Could I say that the radical the square root of 25 times 4 all under one radical, is that the same thing as the square root of 25 separated from the square root of 4? Well, that's a more interesting question, right? But let's think about this. What is the square root of 25? It's going to be 5. And what's the square root of 4? It's going to be 2. And this says, let's just separate into two radicals. Well, if I multiply 5 times 2, do I still get my same answer? Yeah, it's still going to be 10. So that's going to be helpful for something like the square root of 50, okay? So I can take my radical and split it into any product I want, and then I can split the product into separate radicals, okay? So again, helpful for something like 50. 50 isn't a perfect root, but I can split it so that I can find a perfect root that's in there. So for example, 50, when I'm looking at 50, I know that that's the same thing as 25 times 2, okay? And so if I wanted to, I could say it's the same as the square root of 25 times the square root of 2. And the reason I would want to look at it this way instead of just as the 50 is because 25 is a perfect square. So that means this could be rewritten as 5, the square root of 25 is 5, multiplied by a radical 2. And this, in fact, is the simplified form of that radical. So 50, radical 50, simplifies to 5 radical 2. Okay, and I could do something similar here with the 300. I want to look at 300 as a perfect square times an imperfect square, so I could simplify at least part of this number. So for example, 300, I know that's 100 times 3. So the square root of 100 is something I could take, and even though I can't take the square root of 3, that's okay. This gets me a simpler form. So the square root of 100 is 10, and that gets multiplied by my radical 3. So this is going to simplify into a 10 radical 3. Okay, or something like 18, right? 18 I know is 9 times 2. So if I had the square root of 9 times the square root of 2, then this becomes 3 times my square root of 2. Okay, now that's probably the easiest way to do these. So, and I showed you even more work than I would do. When I'm looking at 300, for example, when I'm looking at 300, in my head I'm saying, okay, that's 3 times 100, so I'm going to jump right to 10 radical 3 as my simplified radical. But I don't know if the same thing is happening in your head that's happening in my head. I can look at these numbers, and not all of them, but I can look at a lot of these numbers and figure out what perfect square is hiding in those numbers. But there's a couple things we have to be careful with this process. First of all, you might find a perfect square, but it might not be the biggest perfect square. Okay, let me show you. For example, on 48. Maybe you're looking at 48 and you're like, okay, well, I know 48 is the same thing as 4 times 12. So I could say square root of 4 times square root of 12, and then it would be 2 square root of 12, which is a simpler form, but that one is not completely simplified. And maybe you could see the difference. Okay, here, the number that was left over, the 2 or the 3, or again the 2, that's a prime number, and there's not going to be any way I could break down that prime number. If you look here, 12 is definitely not a prime number. And if we were to continue just looking at the 12, I could say that 12 is 4 times 3. That means there's another perfect square in there. So really, I shouldn't have looked at it as 4 times 12. If I had a 4 and another 4 in there, what I should have said was, okay, this is really 16 times 3. And then 4 radical 3 becomes my answer. It was like, whoa, that's already really complicated, right? Or what if it's a number like 294? I can't even look at 294 and know the biggest square root that's in there. So there has to be another process for us to simplify if I can't just look at the number and find the biggest perfect square that's hiding in it. Okay? So what does the process involve? The process involves making a factor tree. Now I want to show you first with something a little simpler. Let me get rid of some of this. Let's go back to our square root of 50, for example. Okay, if we use a factor tree to break this down, 2 goes into 50 25 times, and then 25 becomes 5 times 5. Once we have our number broken down using a factor tree, what we're going to try to identify are pairs of numbers. And why do we want a pair of numbers? Well, because that pair of 5s represents 25, which is a perfect square. Any pair of numbers, right? If it was a 3 and a 3, that would represent a 9. A 2 and a 2 would be a 4. Or a 7 and a 7 would represent a 49. Any pair of numbers is a perfect square. So if I can find any pair of numbers, that pair represents something I can square root, which would come out of the radical. So this pair of 5s tells me a 5 is going to be able to come out of this radical. And then anything that's not paired up is going to be stuck inside of the radical. Okay, so we want to break the number down using a factor tree, and then we're going to look for pairs. Pairs tell us what can come out of the radical. Anything unpaired tells us what has to stay in the radical. So if we go back to, let's look at this 48 again, okay? If I wanted to break this guy down, because I saw 4, but it wasn't the biggest, let me use my factor tree, okay? 2 is going to go in to 48 24 times, and then 2 is going to go into that 12 times, and then 2 is going to go into that 6 times, and then 2 is going to go into that 3 times. So I've got a pair here, and I have a pair here. If I have 2 pairs, that means I have a 2 that can come out, I have a second 2 that can come out, and then this leftover guy is what's going to stay in the radical. And that all of this is being multiplied, right? So we want all of this to be multiplied as well. So my answer here is going to be 2 times 2, which is 4, outside of a radical 3. Okay? Or with 294, let's take the 294 just again so you can see it. We got to break this down, and when you make your factor tree, it doesn't really matter how you break down the numbers. You can use any products you want, but I like to go in order. So I'll start with 2 if it's even, and I'll use 2 as many times as I can, and then when I can't use 2 anymore, I'll try 3, and then when I can't use 3 anymore, I'll try 5. Right? I'm going to try to use my numbers in order so that all my 2s and 3s and whatever, like, they're all going to line up, and it's really easy for me to circle. Whereas if I had like a 2 and a 3, and then I had another branch over here with another 2 and a 3, then I'm making these weird, like, jelly bean circle things. It's not pretty, okay? So let me just get rid of all that. So if it's an even number, I'm going to divide by 2 as many times as possible. So 2 is going to go into 294. Let's see. 2 goes into 2 once, and then 4 times, and then 147 times. I better just double check that. 294 divided by 2. Yeah, 147. Now 147 is not even, so I know 2 is not going to go in. But 3 is going to go in, And how can I tell by looking at it? You guys know the divisibility rule for 3? Like maybe you know it's even, so 2 goes in. Or maybe you know it ends in a 0 and a 5, so 5 goes in. Or ends in a 0, so 10 goes in. Do you know the rule for 3? If you look at the sum of the digits, so 147, if you added those digits, the 1 plus the 4 plus the 7, you get 12. If the sum divides by 3, which this does, divides by 3 4 times, if the sum of the digits divides by 3, then the whole number is divisible by 3. So 147, divided by 3 is exactly 49. So if you didn't know that trick, maybe that'll help you. Okay, so that becomes 147 breaks down to 3 times 49, and then 49 is 7 times 7. So here is my pair. That pair of 7s represents that perfect square, right? Square root of 49 is 7, so this pair of 7s tells me I have a 7 that can come out of the radical. And then anything that's unpaired stays in the radical. So this 2 would stay in, and this 3 would stay in. And so my final answer is going to be 7 times a radical 6 is what's left over. Okay? So let's go back here. That's not what I wanted. We want to break down the radicand. That is the number underneath the radical. Break down the radicand by dividing it by prime numbers is what I like to do. Okay? Again, let's just go back here. Okay, looking at the 50, I used 2 and 25, so I divided by a prime number first. But if you wanted to take the 50 and say, oh, that's 5 times 10, 5's still a prime number, that's fine. But then you're going to have 2 times 5 over here, and then again you're making this weird like jelly bean circle of the 5s, which isn't a huge issue, but I like to start with the smallest prime numbers and work my way up, just so that it's 2 and then 5, then 5 or whatever the issue is, that all the 2's are going to be lined up, and then the 3's and then the 5's. It's all nice and organized. So I would use 2 as many times as possible, then 3, then 5, then 7, 9, let's see, 8, 9, 10, 11, 13, 14, 15, 16. So I don't think you're going to be dividing by numbers much bigger than that, but I like to stay in order just to make a nice tree, but it really doesn't matter. Okay? So now, when we're breaking down the radical, if it's a square root, I showed you, circle pairs. But what if we had a cube root? Like cube, don't write this on your paper, but cube root of 8 was 2, because that's 2 times 4, and another 2 times 2. Well, if it's a cube root, then we need a group of 3 of those numbers, right? So we're going to circle... thought I clicked the eraser. We want to circle groups based on our index. If it was a square root, you're going to look for pairs. A cube root, you're going to look for groups of 3. A fourth root, you're going to look for groups of 4, and so on. So circle groups of numbers based on the index. The index is going to tell you what to circle. Circle groups are telling you what can come out of the radical, while the ungrouped, uncircled numbers tell you what stays in the radical. Okay? If you have multiple groups that come out, they're going to get multiplied. If you have multiple numbers that stay in, they get multiplied as well, which makes sense because we're using the factor tree. It's just a bunch of products. Okay? So let's look at these. Now again, if you don't need the whole process, like if you're looking at 18 and you know it's 9 times 2 and I can't break the 2 down any further and you can jump right to 3 radical 2, awesome. If not, totally fine as well. So if we were to break this down, 2 goes in 9 times, and then 9 becomes 3 times 3. That's as far as I can go because my last number here on my branch is prime, so I'm good. Broken down. Now I'm looking for, because this is a square root, a pair of numbers. So the pair tells me what comes out of the radical. And anything unpaired, uncircled, ungrouped stays in the radical. So this is telling me a 3 can come out, and this ungrouped, uncircled number tells me a 2 has to stay in. Okay? Now if you put, just want to show you, you can still use your calculator to verify your work. If you put radical 18 into your calculator, it's going to give you a decimal. It's not going to simplify it for you. But if you're saying radical 18 is equal to 3 radical 2, then put 3 radical 2 in your calculator as well. And guess what you should get to confirm that that's actually equal? Is you get 4.24. You get the same exact decimal again. So I will see a lot of times people go, oh, 2 comes out and 3 stays in. For some reason they mix those up. Well, if you confirm right away, right, put in radical 18, put in the opposite one, you can see those decimals aren't the same, which means they're not actually equal. So you can use your calculator to verify that the decimal amounts are equivalent. Okay? Alright, how about 2? So this one is not even, so I cannot divide by 2. But look at the sum of the digits. 1 plus 3 is 4, plus 5 is 9. That divides by 3, which means this number divides by 3. 3 is going to go in, let's see, 45 times. Just make sure, so I don't want to do anything stupid on the note sheet here. 135 divided by 3 is 45. Yep. 45. Then breaks down. And notice how I'm crossing out the numbers as I break them down, just so I know I'm not putting them in any of my groups. So 45 is divisible by 3 again. 3 goes in 15 times. And then 15 is divisible by 3 again. It goes in 5 times. And once I've ended with a prime number, I know I can stop. So now I'm looking for pairs, and I have one. So that pair of 3's really represents 9. And what's the square root of 9? It's 3. So that pair of 3's tells me a 3 can come out of the radical. And then the 3 and the 5 that are left over, they're going to stay in the radical. And if we have multiple numbers that stay in or come out, then we're going to multiply. So final answer here is going to be 3 and then radical 15. Okay? And here's a good spot for you to try if you want to pause the video and give it a shot. Then let's see. 180 is even. 2 is going to go in 90 times. And then 90 is even. 2 is going to go in 45 times. And then we just dealt with 45 over there. 3 goes into it 15 times. And then 15 is 3 times 5. So this time I got a pair of 2's, and a pair of 2's, and a 5. So that's telling me a 2 can come out, and a 3 can come out, and a 5 is going to stay in. So this final answer is going to be 6 and radical 5. Okay? There it is. And again, if you wanted to confirm, let's just put both of these in the calculator. Put in the square root of 180. You get a decimal. And put in 6 times the square root of 5, and you better get the same decimal end we do, so we're good. Alright, so now let's try this with some bigger roots, like cube roots of 48. Cube root of 48, so we're going to break this down the same way. 2 goes in 24 times. 24 becomes 2 times 12. 12 becomes 2 times 6. 6 becomes 2 times 3. There's a prime number, so now I can stop. So now it's a cube root. Instead of looking for a pair, I need a number that's multiplied by itself 3 times. So I need a group of 3, but I have one. So, oops. I have a group of 3 right here. So that group tells me that a 2 can come out of the radical. And then left over in the cube root this time, make sure you keep the index there, is a 2 and a 3. So my final answer here is 2 cube root of 6. Okay? Make sure you keep the index there, because 2 cube root of 6 definitely has a different value than 2 square root of 6. And when you're writing that index, make sure it's written smaller and like tucked into the radical there. I don't want a cube root of 6 to look like this, where it could be mistaken for 3 times the square root of 6, right? That's different than a cube root of 6. So make sure you're writing it smaller and tucking it in there. Alright, let's try the next one. So here, there's a negative. What is that negative going to do? Well, just like we said in the front, that the cube root of 27 was going to be 3. If it was a negative 27, it just made our answer negative. That negative there is just going to make our answer negative. That negative could come right out if we wanted to, right? We could take the negative out. But let's deal with the simplifying piece of this first, okay? Let's break this down. 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. So I'm going to be able to take out a 3, and there's going to be a 2 left over. Now here, got to be a little more careful, because there's already a 2 out here. So in this one, there was already a 2 out here. So I want to make sure that that 2 is still out there. And now I'm also going to be bringing out a 3. And then left over in my cube root, I'm going to have this 2. Now I've got freaking arrows everywhere, but just so you can see where I'm going. My 2 is going to stay. Okay, now the negative can also come out. So my final answer is going to be a negative 2 times a 3, which is a negative 6, and then I have a cube root of 2 left over. Okay, now that looks like a big hot mess. So let me just do it again so you can see it. So we have on the outside of the radical, oops, red. On the outside of the radical, this negative can come out, so a negative here. And on the outside of the radical, there's a 2, which I still want to be outside. And now, because this group of 3's got circled, a 3 comes out. And then left over in the cube root is just the 2. So this final answer becomes a negative 6 cube root of 2. And again, if we want to double check that, let's just put it in the calculator, okay? So originally, we had 2, and then we had a cube root of a negative 54. And I want to make sure that my negative 6 and my cube root of, what did I say, 2 is the same, has the same value, and it does. See how both those decimal values are the same, so I can confirm that my simplified answer is actually equal. Okay? So again, here's, erased. Here's another one for you to try. If you want to pause the video, give it a shot. Otherwise, let's see. 2 goes into this 108 times. 2 goes into that 54 times. 2 goes into that 27 times. 3 goes into that 9 times. And then 3 goes into that 3 times. Prime number, now I stop. Groups of 3. Well, I've got one here, and I've got one here. So that means a 2 comes out and a 3 comes out, and since there's nothing left over, that means nothing left will stay in the radical, which means this answer is exactly 6. Okay? What's going on here is we have a perfect root. If I said, for instance, what's the square root of 64, you could absolutely break this down and say, okay, it's 2 times 32, 2 times 16. I should have picked a smaller number. Let me do this again. Pick a smaller number. Okay, let's say it was square root of 16. You wouldn't break down the square root of 16 because you know the square root of 16 is 4. But let's say you weren't thinking and you're like, oh, I'm doing a factor tree. 2 goes in 8 times, and that's 2 times 4, and then that's 2 times 2. Well, you got a pair, and you got a pair. So a 2 would come out, times another 2 would come out, and that's it. 4 would be your answer. That's exactly what's happening here on this U-try. What we have is a perfect cube root. We're just not as familiar with those as the square roots. So if you're not going to recognize your perfect cubes and you break it down, what will happen if it's a perfect root is there won't be anything left over. And again, this could be confirmed. What is the cube root of 2? Oops. Let's make it a cube root, not a 216th root. I swear I'm pushing these buttons. Okay, so there it is, 6. Okay? Alright, let's try a few more. We've got a 4th root here. So a negative on the outside just means we're going to be multiplying our final answer by a negative, no big deal. What we'll change here is now we're going to look for a group of 4. Okay? So this is 2, goes in, let's see, 81 times. And then 81 becomes 2 times, not 2, sorry, 3 times 27. And then 3 times 9, and then that becomes 3 times 3. So here's my group of 4. And maybe that sounded familiar, right? Because we actually had a 4th root of 81 on the front. So we're going to have a negative. We've got a 3 coming out. And left over in the 4th root is a 2. That's my final simplified answer. And just so we can confirm, we started with a negative 4th root of 162, and now I want to confirm that negative 3 times my 4th root of 2 is the same decimal, and it is. Okay? Alright, 5th root of 210. Same thing now. I just want to look for a group of 5. So 210 is 2 times 105. 3 goes into that 35 times, and then 5 goes into that 7 times, and that's prime, so I can stop. But what happened here? Well, there are no groups. Definitely not a group of 5. There's no groups of anything. So if I don't have any groups that can come out of the radical, what does that mean? Well, it means that everything has to stay in. That means this radical cannot be simplified. It is in the most simple form already. It'd be like if I said simplify the square root of 2. Well, I can't. Square root of 2 is going to be my answer. Okay, that's what's happening here. It's just not as obvious because 210 is obviously not a prime number. But if there are no groups, then everything stays in the radical. And if everything stays in the radical, then you have the exact same radicand that you start with. So 5th root of 210 is as simplified as that gets. Okay? Why does it look so sloppy? I'm sorry. It's because it's the bottom of my iPad where I'm writing here, and it's like my hand is falling off the edge, and I know you don't care, but I'm just trying to make excuses for myself. Alright, last one. Last one again, one for you to give it a shot if you want to pause and try it. So square root, so we're back to looking for pairs. So 2 goes in 64 times. Now, I just want to say that this is where I would stop. Now, I know 64 is going to continue to break down, but I know the square root of 64. What's the square root of 64? It's 8. So I already know this is going to become an 8 with a radical 2 left over. Now, if you want to keep going, you can. What's going to happen? Well, this becomes 2 times 32, and this becomes 2 times 16, and that's 2 times 8, and that's 2 times 4, and that's 2 times 2. So you got a pair, and a pair, and a pair, and a leftover. So if a 2 and a 2 and a 2 come out, and a 2 is left over, it's a lot of 2's, then 2 times 2 is 4 times another 2 is an 8, and then radical 2. So you get the same thing, but if you see your perfect square a little sooner and you want to stop, by all means, okay, stop. And I would have probably done that let's say here as well, because I know my perfect cubes. I already know 27 is a perfect cube. The cube root of 27 is going to be 3. So if you wanted to stop there and say, oh, this is going to be 3, and then there's going to be a cube root of 2 left, then you'd be totally fine. Just don't forget about the 2 on the outside and the negative. Okay? So up to you on how far you want to take some of these, but at least now, hopefully, you have a process to help you through if you can't see any roots that are hiding. Okay? So if you got some practice to try out, give it a shot, and then as always, if you're struggling, just reach out. Alright, guys.